Let's take a look at how you work out the Unit 9 Applications of Thermodynamics practice questions included in the A+ College Ready curriculum. Number 1 is simply a question about what is entropy after all. Entropy is one of the laws of thermodynamics, and it talks about how energy and particles both become more disordered over time. Particles and energy becoming more disordered is, of course, the answer. Choice D is partially correct in that entropy does explain that heat becomes more and more distributed instead of being concentrated in things like stars, but it doesn't address the idea of particles also becoming more and more disordered. In Unit 6, students learned how to do delta H by doing all the products minus all the reactants, and this is no different. This is just delta S, the change in entropy, and so we do all the products minus all the reactants. And when we do that math, we get the final answer, negative 112. Number 3 is the same setup, except number 3 involves many more numbers. So the setup looks like this. We've got all the products in blue, all the reactants in red, and when you do the math, you get, and then the final math, you get negative 432.4. It's important that students take the time to practice these very complex problems to make sure they're not dropping signs and make sure that they're getting the correct answer. Same setup as before, all the products minus all the reactants. So there's the setup, and then finally the math and the answer. You can do this not only for delta S, but you can also do it for delta G. To find the delta G for the entire reaction, we take the delta G of formation of all the products, again, minus the delta G of formation of all the reactants. And there's the setup, and there finally is the answer. Number 6 is the exact same setup, all the products minus all the reactants, and you get negative 1108. Same type of question, all the products minus all the reactants, and you get an answer of negative 166. Notice, however, that the delta G's were in kilojoules and the delta S is in joules. This becomes important later on. For number 8, there's no math involved. It asks the students to think about what's going on. So first, let's look at delta S. You're going from a solid to a solution. So as a solid becomes a solution, we're going from more order to more disorder. Therefore, delta S would be positive. So now we're locked into either A or B. Now to look at delta G, the ammonium nitrate does dissolve in water. Since it does dissolve in water, we know that it had to be thermodynamically favorable. For a thermodynamically favorable situation, delta G is negative. To do number 9, we have to find the connection between delta G and K. So first, to find delta G, we take the information from the table and find delta H. We take the information from the table and find delta S. And then we plug those values into the delta G equation. And we get a delta G value of negative 139 kilojoules per mole of reaction. Now we have to link the delta G to the K. That's this equation. This time when we plug in the value for delta G, we have to make sure it's in joules because the R value off the equation sheet is 8.314 joules per mole Kelvin. So that means the delta G also has to be in joules. The temperature has to be in Kelvin, and then we solve for the natural log of K. To find the value for K, we do the inverse natural log, and we get a K value of 2.37 times 10 to the 24th. Number 10 is very similar, except this time we're going backwards. We're going from a K value to a delta G value. So we plug in everything we know into this equation. The delta G comes out as 1,818 joules, but notice that the question asked for delta G in kilojoules per mole, so that would be 1.818. This is very similar to the previous problem. We can use the information to find delta H and delta S. We plug that into the delta G equation. We get a final answer, and then we plug that into the delta G equals negative RT ln of K, remembering to make it joules, not kilojoules, and we solve for the natural log of K. Then we take the inverse natural log of 36.8 and we get that number. Number 12 is similar to the ones we've worked previously. This time we have a K value of 5 times 10 to the 8th. For this one, work on, first of all, what should the sign of delta G be? It becomes a thought process. K is much larger than 1. If K is much larger than 1, then the reaction should proceed towards products, which means it is thermodynamically favorable and delta G should be negative. So let's see what happens when you actually plug in these numbers. You get a delta G value of negative 50, which makes sense because K is so large. For number 13, we switch modes to redox reactions. The first thing you want to do is assign oxidation numbers and then look what is the change in oxidation state. And we can see that the manganese is going from a +7 to a +2, which means that it is gaining 5 electrons. Manganese's oxidation state is becoming more negative, which means it is being reduced. So we need 5 electrons on the reactant side, and that explains the change from a +7 to a +2. For number 14, if we look at the oxidation states in the equation, zinc is going from a 0 on the reactant side to a +2 on the product side. So zinc is being oxidized, which means copper ion is being reduced. That would make both B and C seemingly correct. But remember, the question says, what happens at the anode? We teach the students an-ox, which means at the anode, oxidation occurs, and red cat, at the cathode, reduction occurs. So at the anode, oxidation is occurring, which means the correct answer must be B. As the copper ion in number 15 is changing into solid copper, what would happen in the copper half cell? Well, as that copper ion plates out on the surface of the copper electrode, you would expect that the copper electrode would get heavier and heavier. The zinc electrode, meanwhile, would be getting smaller and smaller as the zinc turns into zinc ions. So therefore, the correct answer has to be C. The copper electrode would increase in mass. For this equation, we know that one of them has to be flipped. We also know that it's a galvanic cell. In a galvanic cell, the E of the cell has to be positive. So we can either do this way, or we can do this way. We either flip the 0.76 to be positive, or we flip the 0.80 to be negative. Notice that only one of those choices, the blue choice, gives you the correct answer of positive 1.56 volts. And remember that in galvanic cells, the voltage has to be positive. So if we flip the zinc equation, the balanced equation looks like this. That means the electrons are leaving the zinc, and as zinc is being oxidized, and traveling to the silver, where the silver ions are turning into solid silver. So that means the electrons are leaving the zinc half cell and traveling over to the silver half cell. For this, we have to use the table and actually calculate E naught for each one. Thermodynamically favorable means the same thing as a positive E naught. So if looking at all the answers, the only one that gives us a positive answer would be 0.78, and that would show a galvanic cell. All the other ones would be electrolytic cells because they are not thermodynamically favorable. For number 19, you want to pick the oxidation with the greatest positive number, and then you want to pick the reduction with the greatest positive number as well, which means combining the iron. You want to combine the iron with 0.77 with the manganese, which is 1.18, and the manganese would flip to be positive 0.18, giving us a greatest overall value when added together. For number 20, first we need to write the equation so we can identify what's going on. The copper is going from a +1 state to a 0 state. That's a change of 1 electron. The cadmium is going from a 0 state to a +2 state. That's why we multiply the copper by 2. So if we look at it, the copper is being reduced as it goes from a positive to a 0 state, and the cadmium is being oxidized as it goes from a 0 to a +2 state. At the cathode, red cat, we know that reduction occurs. So the one in which reduction is occurring is the copper, as it goes from a +1 state to just a 0 state. Since reduction is gaining electrons, then the correct answer would be D. This ties in with the previous question. They want to know what would the actual reading on the voltmeter be, and the setup is we take the positive 0.77, we flip the 1.18, and we get 1.95. N is the number of moles that are transferred in an electrochemical cell. So if we look at what's going on, there are two irons, each losing one electron to become iron with a 2+. One manganese gains 2 electrons. The reason why we had to put a 2 in front of the iron is to balance out the electrons lost with the electrons gained by manganese. So how many total moles of electrons are being transferred? Just 2. The salt bridge functions to maintain charge between the two half cells. If there was no potassium nitrate in the salt bridge, just replaced with deionized water, there would be no charges that could balance that out. And that means it would not work. The voltage would become 0. To identify what's going on in number 24, we really need to assign oxidation numbers. However, the choices only talk about bromine, so I'm only going to assign oxidation numbers for bromine. It's going from a +5 to a 0 state. That means it's gaining electrons, and gaining electrons is reduction. The only answer choice that suggests reduction is letter D. This is a slightly different twist on a question. They're giving you the E for the overall cell as being 0.9. Therefore, 0.9 is equal to the negative 0.76 plus whatever the oxidation reaction is. Do the math and you get 1.66 volts. Now, understand that that is the oxidation reaction. However, the target reaction is reduction. So, in order to find the target reaction of reduction, we need to flip it, and therefore the reduction potential becomes negative 1.66 volts. This is all about reading a diagram and figuring out what's going on. First of all, there's a voltmeter present, which means it's a galvanic cell. An electrolytic cell would have some kind of power source. They try to give you some clues about what's going on. When the switch is closed, the mass of the tin electrode increases. What that implies is that the tin ions in solution are gaining electrons, being reduced, and forming solid tin, so that over time there's less and less tin ions and more tin solid. So which electrode is the anode? An, ox, and red, cat. So at the anode is where oxidation occurs, which means that it must be the metal X. This is similar to that other question where we're given the voltage for the cell as 0.60 volts, and we know that the tin has an E naught of negative 0.14, so we can find the oxidation number as 0.74 volts. However, notice the X3 to X electrode is not oxidation, it's actually reduction, which means that we need to flip the sign and it's negative 0.74 volts. Number 28, please encourage students to see what is the difference between all the answer choices. Notice that the 96485 and the 0.60 are all the same. Therefore, that doesn't matter. We're using this equation. This is a way of asking a multiple choice question in a format that doesn't force them to do complex math. So looking at the two half reactions, the tin is gaining 2 electrons, the X is losing 3 electrons. So it comes down to what is the least common multiple, what number do 2 and 3 have in common, which is 6. Therefore, the delta G would be negative 6 times F times E, and that correct answer would be A. 29 has to do with the Nernst equation, so let's remind you what that looks like. Basically, the E of the cell is influenced by both temperature and also by the reaction quotient, which is products over reactants. So if the tin is changed from 1 to 2 molar, in the standard conditions at E naught, all molarities are 1 molar. So what happens if we change it to 2 molar? So to calculate Q, we would look at the equation and figure out products over reactants, and you would come up with 1 over 2. Remember, we don't include pure solids, so the X and the 10 don't actually show up in the Q expression. Since Q is less than 1, then there are more reactants than there are products, and so the E of the cell will be greater because there are more reactants. You could actually plug in 0.5 into the Nernst equation with a calculator if you have that ability, but it's also important to realize that when Q is less than 1, E becomes greater, and that when Q is greater than 1, E becomes smaller. For number 30, this is a galvanic cell. It is occurring. This is a thermodynamically favorable reaction. In a thermodynamically favorable reaction, reactants turn into products. Since products are favored, K has to be greater than 1. We know that for a negative delta G, K is greater than 1. This is, again, reading what's going on and finding clues. As the cell operates, copper metal is deposited onto one electrode. Notice also that there's a power supply, so this is an electrolytic cell. So what's happening in the cell is that the copper ions in solution are gaining electrons and becoming solid copper. Therefore, the copper ions are being reduced and forming copper, which means the electrons are going from the right-hand electrode over to the left-hand electrode, which gives us answers either C or D, and letter D indicates that copper is gaining electrons, which is what the diagram suggests. So looking at the equations from the previous problem for number 32 down here, what is the overall correct balanced net ionic equation? Just realize that the copper is showing 2 electrons, whereas the oxygen is showing 4 electrons. In order for electrons lost equal to electrons gained, we're going to have to multiply the copper by 2. We also know that it's an electrolytic cell, and so we want the E naught to be negative. So we can actually answer both 32 and 33 together. We need to flip the oxygen equation to give us an overall negative E. And since we're flipping the oxygen equation, that means the water is going to end up on the left-hand side, and we will multiply the copper ion by 2. So we're looking for an equation with water on the left-hand side and 2 copper ions on the left-hand side, and that choice is C. You get a 2-for question by finding the answer for 33 and then figuring out what 32 is. For this, we need to know what exactly is 2.0 A. An amp, or A, is a coulomb per second. So since that is coulombs per second, our first job is to change 40 minutes to seconds, and then use the idea of an amp as being equal to a coulomb per second, and then do the math. Realize that this is mental math. There is no calculator allowed here. So one simple way to do that is to separate out all the non-zeros and get 2 times 4 times 6. And then notice that there's a 0 in 40 and a 0 in 60, so I can take that to make 100. So I end up with 2 times 4 times 6 times 100 is equal to 48 times 100, which is 4,800. Be sure you work with students on mental math for problems like this. An electrolytic cell in number 35 is not thermodynamically favorable. After all, cell phones don't charge themselves. We need an answer that says thermodynamically unfavorable, and we know that in such a case, delta G is positive, so the answer is A. We know that the K value, or equilibrium constant, is quite large, which means this reaction does happen, which means delta G is 0. We also know that when something is thermodynamically favorable, the E naught is positive. So we're looking for an answer where E naught is positive and delta G is negative. Letter A. For number 37, again, this is a Nernst equation, and it's just asking you to identify what happens when you change concentrations. So we've got to flip one of them, and the overall reaction is this. We flip the manganese equation so that when we add them together, we come up with an overall positive answer. Q, therefore, will be the manganese ion concentration over the cadmium ion concentration. Remember that we would not include the solid manganese or the solid cadmium because we don't include pure solids in Q expressions. So when we plug in the math, we get 1 over 5 is equal to 0.2. And when Q is less than 1, then according to the Nernst equation, there are more reactants that are products, and then E should get larger. So we're looking for the voltage will increase in the cell because Q will get smaller.